After we learned how to get the how to estimate a population proportion, now we're going to learn how to estimate a population mean. So estimating a population mean. At the very beginning, we're going to review what is the symbol we use for population mean. Meal, right? And what do we know usually? We have a sample mean, which is x bar. And if you learn that in this, x bar is the unbiased point estimate, right? X bar is an unbiased point estimate for population mean. And there's some other letters, sample size, which is n, and the sample standard deviation, that's S, letter S, and but the population standard deviation is sigma. Okay, there's one more is the margin of error. It's just an E. Okay, it's very similar. All right, now I'm gonna show you. I'm gonna tell you a flow chart about the distribution. Which one you're gonna use? Okay. Now the first one, simple random sample. Simple random sample. Okay. If it's yes, it's going that way. If it's no, then I tell you what to do later. Okay. If it's a yes, then the next question is population normally distributed? I just say normal. Is the population normal? And that answer could be yes, could be no. Yes, could be no, or unknown. Okay, and then the next one you're going to ask yourself is n greater than 30? Okay, the answer could be yes. Large, okay, could be no. Okay, if the sample size is large, or then that go to, because both go to here. Okay, then that's sigma known. In most of the case, we don't know the population standard deviation because you only have a sample. You want to use a sample to estimate the population. You want to use the sample mean to estimate the population mean. So how do you know the population standard deviation? If you think, yeah, you don't know that. However, you might have yes, because based on the previous experience, or you might have a no, okay, or unknown, or totally unknown, have no clue. So this, oops, sorry, you're going to use T, and this you're going to use Z. Sorry. All right, so that's the little tricky part. Okay, and then if it's not a simple random sample, here, if it's not a simple random sample, and if the population is normal, no, it's not normal, and it's a small sample size, then here we're going to use other methods, which I'm not going to talk about that here. Okay, so now you see this T and a Z. We know Z is normally distributed, and what about T? T is a new distribution that we're going to learn today. Okay, here is Z. We know this. We're very, very familiar with this, right? Bell curve, symmetric, center 0, standard deviation 1. That's the standard normal distribution. For t, it's also bell curve, centered at 0, and that is a t. You might ask, looks the same. Yes. However, t has different shapes, depends on the degree of freedom. That's the df. Okay, what is the df? That's the degree of freedom. That's a new word, degree of freedom. So when the degree of freedom goes from 1 all the way to infinity, okay, and then this shape, this t distribution shape will go from a flat, very flat distribution like that, and then go to, what is this? This is z, this is normal. Okay, so the shape of this t curve changes when the degree of freedom change. So did you notice that, when we have the degree of freedom 1 and 2 and 3 and 4 for each integer, we should have a different table to give you the probability. However, most of the time we don't really care about the little detailed table, just like the z table we have. So we usually use this one. We use this t table. Okay, I want you to take a look at the t table, and if you can Google it, you just find the t distribution or t table. There are plenty of the websites will give you this table. Or if you go to the end of any statistic textbook, there is a table there, t table. Looks very, very similar to this. So I just use this one as an example. Okay, so this is the t table, that's the t distribution. Did you notice that here is a df? So the very left column is the degree of freedom. That's from 1, 2, 3, 4, 5, and all the way. And this table give you somewhere to like a 30, 40, 60, 80, 100, and 1,000. And did you see at the bottom is a z? That's a normal. Now let's look at this. It's called a cumulative probability, which is the area to the left of that t value. So to the left, let's look at a 0.975, this one. And then did you see this one tail and the two tails? Did you see this too? So one tail is 0.025 and two tail is 0.05. What does that mean? That means for the t distribution, and they give you this 0.975, and what is this little tail? It should be 0.025. That's one tail. That's one tail mean, okay, 0.025. If it is for two tail, then here's like 2.5%, and here's another 0.025. So two tail will add up to 0.05. That's what it say here, 0.05. So this 0.05 is corresponding to 95% confidence interval. Okay, so that's 0.025 to one side and 0.025 to the other side. All right, then the degree of freedom. Did you see that for each degree of freedom there is a number in this table, and this is called a critical value. This critical value, you might notice that when the degree of freedom, even for like a 95%, okay, 95% confidence interval or two tail 0.05, degree of freedom 1, 2, 3, 4, 5 goes from 12 point something to 4 to 3 to and all the way down. When the degree of freedom is 1,000, that critical value is 1.96. Hey, it's very close to what we're familiar with, right? The z is 1.96 if you remember, for 95% confidence level, and we have 1.96 as our critical value. So you get the general idea about this. All right, now let me ask you a quick question. Example 1. Okay, can you find TF over 2 when it's 95% confidence interval, or your confidence level, for n equals 6? Can you find it? This note is a little different than this note. So you will find out what's going on later, okay? So don't worry. And here, let me tell you one important formula we have here is the degree of freedom equals n minus 1. So in our case, we're looking for 95% confidence interval and n equals 6. So the DF should be 5. And then you can do is find the confidence level 95% at the bottom, and then you go all the way up to the degree of freedom 5. So you can find 2.571. Therefore, your T alpha over 2 is 2.571. You might have noticed that in this case, our alpha is 0.05. So T alpha over 2 is actually T 0.025. And in our book, this alpha, this little number, shows the area to the right of this T value. But in this table, it shows the cumulative probability. So that's to the left. So don't worry. This might happen when you look at the different tables. Then they might have a little different notation. But once you know it, it's no big deal. You can always find the right number. So that's our critical value in our first example. Okay, I'm going to work on the example 2. Example 2 is, you know, the candy, okay? the weight or the weights in grams of randomly selected Reese's peanut butter cups miniatures. So it was like all those little candies, right? All those little candies. So for each bag, there are 38 cups. And they claimed the total weight is 340.2 grams. Okay, so that's what they claim. They print that out on the label. However, you don't know whether this is true or not. So what you did is you randomly select, simple random sample, you simply just randomly selected 6 cups. And then what do you get? You weigh them, okay? So you have 8.639 grams, and you have 8.689, right? You do this, okay? You have a very, very precise way. I assume that you have a little scale that can help you to get this. And 8.936 and 9.042. That's your sample. Simple random sample. Now, question number 1. Okay. Can you find the point estimate of mu? Point estimate of mu, of the population mean. And this population mean is for all those cups, what's the average weight? And if you use a 340.2 divided by 38, so 340.2 grams divided by 38 cups, what you should have, if you use your calculator, it should be 8.953 gram per cup. Okay, if their claim is right, the mean should be just like that. But we don't know. So we have this sample, and then we find the point estimate of it. So the point estimate of mu should be just x bar. How do you get x bar? You just add all the x together divided by n. You add 1, 2, 3, 4, 5, 6. You can add all those 6 numbers together divided by 6. Okay, you can pause and then you can start using your calculator to add 8.639 plus 8.689 plus, and then you add all of them, and including the last one, okay, and all together divided by 6. All right, when you finish, you can check with my answer is 8.953 gram per cup. That's my sample mean. My sample mean is 8.952. and here they should be 8 point, oh sorry, no, that's not right. It should be less than that. Sorry, I did 8.8057. Yes, I tried that. You use your calculator to find the average. It's 8.8. They claim it's 8.953, and what we have is 8.8057. We know this is the best point estimate for meal. Apparently they're not the same, but can I construct a confidence interval so I can have the confidence? I can have like 95% of the confidence that the population mean it's somewhere between two numbers, and to see whether this guy is in my confidence interval or not. Okay, so let's do that. So I need to find the 95% confidence interval for meal. How should we do that? Of course, it's going to be x bar minus e, x bar plus e. It's very similar, right? And what is the e in this case? The e should be either z, alpha over 2, standard deviation over root n, that's this many standard deviation, or t, alpha over 2, s over square root of n. See? If you know sigma, you use z. If you don't know, you use t. But let's go back to our original. Make this a little bit bigger so you can see better. Okay, we want to check. Is this a simple random sample? Yes, we got 6 cups. Simple random sample. So the answer is a yes. Is the population normal? I don't know. However, in this section, when you work on the homework, and I will not ask you to assess the normality, and we just assume it's normal, okay? Because we will, I'm not going to test you, or I'm not asking you to run the normality test. So we just assume it's normal, okay? So we just assume it's normal, and then we go here to here. If it's no or unknown, then you go to the other side. And how do we know that? Either the question tells you that the population is normally distributed, or you can do the normal test, the normal plot. If you remember, it's going to be the x value, and then here is the z-score, and if all the numbers are roughly on a number line, on a straight line, then we say, oh, it's normal. In this case, I think we can do that, and it's roughly on a straight line. However, it's not required, so we just assume it's normal. Now, when it's normal, we go here, and then the next question is the population standard deviation known? Of course it's not. We don't know. We're going to use t, so we're going to use this one. But in order to use t, or to plug in this e here, you have to have a standard deviation, and we know n is 6. And as if you have the data, you have 6 numbers. Do you know how to find the standard deviation? Quick remind, here is the x. You have all the x value, right? So here you get x bar, and here you're going to get x minus x bar, and then you find what's the difference. If you add up, that should be 0. And then the next one, you go x minus x bar square, so you square off this guy, and then you put all the 6 squares. You add up here, and then you're going to use the sum of x minus x bar square divided by n minus 1, and that is your sample variance. So your sample standard deviation is just the square root of this. Phew! So that's like, it's a long process, and because our x values we have was like a 6 numbers, 8.639 and so on. So they are very big numbers. I mean, they're not big, but they're complicated. So let me just do that for you, okay? So I used my calculator. I did this. I did the S equals. So you don't have to thank me. I just give you this. 2054G. All right, now we know sample size, 6. We know S So that's E, and we know X bar. See, we know X bar. So we just should plus and minus this guy. And what is this? That's your critical value. Do you remember we did that? For 95% confidence interval, and we have the degree of freedom is n minus 1, which is a 5. Do you remember what is that TF over 2? 2.571. If you forgot about this, you can just go back to our first example, 2.571. Therefore, our 95% confidence interval, or you can do this, you can do X bar minus E, and our X bar is 8.8057 minus 2.571 times, okay, and here should be S as is, I already give you that, it's 0.20 over 6, and the other side is 8.8057 plus 2.571 and then 0.2054 over root 6. Okay, it's a little complicated, isn't it? Or what you can do is you can calculate this much first, which is your E. Then you just use this minus E and this plus E. And your answer is 8.5901 to what? To 9.0213. Of course, they're in grams, right? So this is your 95% confidence interval for the population mean. Based on your sample size 6, you find this. And what do they claim? I don't know if you remember. What do they claim? Where's my page? Okay, so they claimed it's 8.953. Is this 8.953 in my interval? 8.953. That's what 53. That's what they claim. Okay, is this guy in this interval? Yes, it is. So what does that mean? Because this is what they claim, right? In the confidence interval, the confidence interval do contain the desired mean. It does contain this. So the package appears to have been filled with candy in an acceptable way. So we're okay with it. If our confidence interval is somewhere, but this guy, the desired mean is not there, so we're going to say, wait a second, we probably need to talk to them, okay? Maybe there's something wrong with the factory, so we need to talk to them, okay? So once you have the flow chart and you have enough information, and then you're going to be able to calculate the confidence, construct the confidence interval. Now, very, very similar to the population proportion question, if I give you the confidence interval, if I give you the confidence interval, which is the lower limit and upper limit, if you add these two together, divided by 2, you get the middle number, which is just your X bar, right? That's your sample mean. And if you use the upper limit minus that, you're going to get the maximum error. So I'm not going to go to the detail about this. This is very similar. Or you can use the upper limit minus the lower limit and then divided by 2. You also get E. No, I don't want to do that, but I want to focus on something next is important, is the sample size issue. Find sample size. In order to find the sample size, it depends. If sigma is known, then we're gonna have this, right? We have E equals Z alpha over 2, and we have sigma over square root of n. Now I'm gonna use this E divided by Z alpha over 2. That's sigma over square root of n. So square root of n, if I flip it, Okay, I just flip the numerator and denominator. I get this, and then I multiply by sigma on both sides, and then I take a square, so I get the n equals this z alpha over 2 times sigma over e square. So this is the formula when sigma is known. And if sigma is unknown, you can take a little note here, okay? If sigma is unknown, then we are going to use t, isn't it? Yes, very good. So we're going to have e that will be t alpha over 2 s over square root of n. And very similar to the same process here, our n will be t alpha over 2 times s over e squared. Now, the same question happens is, how do you know the sample standard deviation before you figure out the sample size? So we rarely use this. Most likely we're going to use this one. So we just assume that we know standard deviation. We know the population standard deviation. This one, you just keep in mind, we don't really use this very much. Okay, now let me give you another example. Can make it a little lower so it gets big. All right. Assume that we want to estimate the mean IQ score for the population of statistics students. Okay, so we want to estimate the IQ score. So that's the mu of the IQ for all the stats students. Okay, how many statistics students must be randomly selected for IQ test? So we're looking for n. Okay, and if we want to be 95% confidence that the sample mean is within 3 IQ points. Within 3 IQ points, that's E. E is 3. 3 points of the population mean. Okay. Wechsler IQ tests are designed so that the standard deviation is 15. Hey, that's this. Once you know the standard deviation is 15, that's a population standard deviation. Okay, do you know how to do this? We know confidence interval, we know E, we know sigma, and we know we're going to use Z. And a Z alpha over 2 for 95% confidence interval. What is your Z? You should know this immediately, 1.96. If not, then I hope that you can go back to the previous section for Z alpha over 2 and the confidence level here, confidence interval. Okay, if I want to be 95% confidence, I want to be 95% confidence, I want to be 99% confidence. So here is 1.96, here is 1.645, here is 2.575. So those 3 critical values you should know by heart. Okay, so for 95% confidence interval, then our Z is 1.96. The formula, do you want me to write the formula here? N equals Z alpha over 2 times sigma over E and square. All right, so that will be 1.96 times the standard deviation, which is 15, and the maximum error is 3. So I will go this square. That's going to be easy one. So that's 96.04. Okay. That's a sample size. Are you going to take 96.04 students? No, you're going to round up. Always round up. So n should be 97. Even here is 04. You cannot just ignore that because 96 is definitely not enough. So you always, again, I wrote this, I think, in my previous video too. Always round up when you try to find the sample size. Always round up to the next integer. So that's your answer. N is 97. All right, so among the thousands of statistics students, I don't know, there's a lot. So we need to obtain a simple random sample of at least 97 to find their IQ score. So with a simple random sample of only 97 students, we will be 95% confident that the sample mean X bar is within 3 IQ points of the true population mean. Okay, so this is the how to estimate the population mean.